Welcome back to the Machine Learning in Production Reading Group. We are on Chapter 6 of Designing Machine Learning Systems by Chip Wynn. I'm really excited about this chapter. It's on model development and offline evaluation. And as Chip notes, making models, training models, and sort of debugging them and evaluating them is actually kind of like the most fun part of being a machine learning engineer. The model optimization was what I did my dissertation on, and then I worked at Weights and Biases, which does experiment tracking and versioning, and those are both topics that we cover in this chapter. So this is definitely one of the closest ones to my heart. So I've got lots of strong opinions on some of the things in this chapter, mostly in agreement with Chip. But yeah, are there any particular topics anybody wanted to cover? I can also just do a quick overview from this table of contents. So, two things are squished together in this chapter. We've got model development and training, which is sort of like picking an architecture and a technique, then developing that into an actual working model, which usually involves some form of training. We mostly have deep learning in mind when we're talking about these systems, but to a lesser extent also, random forest, gradient boosted trees, which also have a training phase. Neural networks have lots and lots of hyperparameters, especially, and take a much longer time to sort of like work through, pick those hyperparameters and develop. So that phase, you generate a lot of sort of meta information about what you've tried, what worked, what didn't work, what code you were using at each point, and which data artifacts you were using. So that's the experiment tracking and versioning section. There's some consideration of distributed training, which is super important for really large models, especially in deep learning, splitting data across multiple GPUs. If you're really at scale, you need to split your model across multiple GPUs, possibly both. And a section on automating this whole model development and training process with AutoML, which is something I've never personally tried to use that much. I read the research a little bit, but don't try this hard AutoML that's mentioned at the end that much. And then once you have a model, you need to know, like, there's some kind of evaluation of the model the whole time while you're building it. But then there's like increasingly this separate phase of really hardcore evaluation of candidate models once you've reached the end of the normal model training and development phase, that looks like kind of like deeply interrogating a model and understanding what it does well, what it does poorly, what its biases might be. And this is as models get more and more complex and the data that they work on gets more and more complex, both in the inputs and the outputs, this kind of offline evaluation becomes ever more important, because the gap between what our loss functions can incorporate into our models and what we want our models to do gets bigger and bigger. And so there's more scope for evaluating models outside of just the pure like loss functions, regularization, and architectural choices that we make. And so sort of building a model card, if you've heard of model cards, which I think that was Timnit Gebru who came up with that idea at Google, but these model cards, these explanations of your model, go into great depth about how it succeeds and fails, how it works on slices and chunks of your data. So this offline evaluation thing mixes kind of unit testing and end-to-end testing of your model and associated machine learning system with sort of like building and writing a model card. So that's my summary and overview of the chapter. If I missed anything, let me know. Or if there's something you want to talk about in particular out of all of that, we can jump onto one of those.
I guess there's one thing towards the beginning where it said there's paragraph about deploying two models in parallel, where your non-traditional ML algorithm performed better than your neural network at the start, but the team decided to deploy both at the same time. And then later on, maybe a couple weeks later, when the team received more data, the neural network did better. And then
Mm.
my assumption is they probably switched to that at some point. I thought that was an interesting point that I'll remember to do in the future. Kind of like hedges your bets. You can get good performance now and still prepare for the future.
Yeah, yeah. So that's in our 6 tips for model selection. So that's towards the beginning there. There's this kind of like 6 like heuristics, or maybe like like it's mostly actually kind of like common pitfalls. And one thing I actually did really like about this section was that a lot of them are kind of paired with a real example. Um, drawn from Chip's interviewed like a lot of folks in the ML world about what their experiences have been in the trenches building ML powered products. And so these are like real examples of successes and failures. And so point four is the one Dan was referring to, good performance now versus good performance later. It is kind of a thing where you might have to really reevaluate which model to use. If you're really in like a performance critical every few percentage points or every few even individual cases that are correctly classified or correctly predicted, is if that's super critical, then you might want to really regularly be rerunning your entire model training pipeline, for example, to retrain candidate models, even the ones that you found that you didn't want to deploy in production. So that's based off of this example that said maybe a tree based model will work now when you're kind of data starved, but in 2 months, a neural network might perform much better when you've got maybe a whole ton more data. And they suggest using these learning curves here. This is an example of, as you keep adding more data, how are the like training and validation and maybe other metrics about model performance, how are those changing as you add more data? Some things are really nice and smooth, like this curve. With large language models, people have found that the overall loss maybe looks really smooth, but then that's kind of hiding the fact that there's a bunch of individual smaller things where at a certain point, a certain amount of data is enough that the network will just suddenly learn a new skill. And so there will be big jumps in capability at specific points if you're doing like a really difficult task like language modeling. So these learning curves at a high level can tell you that your model is kind of getting better. If you really trust your top level metric, they're useful. Maybe there are some smaller things you want to cut out, like has my model figured out how to handle fog if it's a self-driving car model? Maybe I want to look at that as a separate learning curve as more data comes in. So I guess this sort of just suggests you want to take a really general idea around your model development. Like, you don't want to just say, "Oh, neural networks don't do well on this problem," just because they didn't work well when you were building your MVP in the first quarter, while you're building this model. Because 6 months later, the neural network might do better, and that's this actual example here. I guess this is the exact example that Dan was referring to about collaborative filtering, which is a recommendation system method that's, like, a little bit more classical, that once they deployed this model in production and got it working, they were able to use additional user data and the behavior of this collaborative filtering model to help bootstrap up that neural network. When people set up these systems in production, they kind of try and get it so that as the system is running, it generates more data that can be used to train additional models rather than just like throwing it out there and having it just run and not setting up a way for the system to, if not necessarily continually improve automatically, that's much harder, at the very least, collect up additional inputs, maybe send some fraction of them off to labelers, or otherwise create what people sometimes call a data flywheel, a process by which collecting data allows you to improve models that allow you to deliver a better experience, or grow your company or improve your technology that then allows you to collect more data and improve further. So a very different style of model development than what you see in an academic context where you just have kind of like a fixed data set, a benchmark that you develop towards.
So this example, I mean, I was a little confused by this example because I mean, the two things here, right? One is that let's say you, like you have, I don't know, like an order of magnitude more data, and now suddenly a much stronger class of models, like neural networks works. But I think that is not what was pointed out in the example. It was like a simple neural network. I don't know exactly what simple means here against a collaborative. I mean, does it mean like, I don't know, like single layer 2D? I don't know what that means. Here, what was pointed out was more of a continual learning thing is what it looked like to me, as opposed to, what previously was talked about, which was basically, like if you have more data, you have, a bigger model might not work if you have smaller data, but then if you collect data, it will work better. That's going to improve. So yeah, I mean, I guess one question I had in mind really was what continual learning gear really means. Is it like there are these online learning, like regret bound type methods, which definitely you didn't, there was this problem of you couldn't train neural networks in an online fashion really because there would be all this catastrophic forgetting and all of that. And so I don't know. I mean, I'm really curious to read more about this chapter, which I think is going to come in chapter 8. Like, what exactly is that going to cover? Is it about training deep neural networks in an online fashion?
Yeah, I think there is stuff about training deep neural networks in an online fashion and making that work. You're right to point out that I think one of the really important points in this example is that the network is able to be continually trained. And so as new data comes in, it's getting updated. And so keeping track of the distribution as it is shifting over time, as the inputs, the labels, or the relationship between the inputs and the labels is changing. I don't know a ton about collaborative filtering. It's a little surprising to me that you can't do like low rank updates are not easy to do with collaborative filtering. But one of the claims here is that being able to easily do continual learning also fits in this, performance at the very beginning of deployment is not predictive of performance after something's been deployed for a long period of time. But as Aman pointed out, it's not easy to do continual learning in very many cases. There's relatively simple things like multiplicative weights and regret bounds, as Aman mentioned, for bandit models. But for something like neural networks, it's much less clear. So I'm also looking forward to seeing what techniques come up in chapter 8.
I mean, I took this as how do you, if you have you're running on a system, say the Tesla car, and you do your self driving vision algorithm, how do you keep the continuity when you have a new idea? And this paragraph or section reminded me about, I think Andre was talking about how they do shadow mode, where they have
Yeah.
the original algorithm that's in production, and then they have these new ideas. And how do you like make that change seamlessly? Well, they're gonna run their new algorithm in shadow mode where it sees the same data, and then they're gonna check the performance on that. And then when they're sure or they have enough confidence that the new algorithm works just as good and better than the old algorithm, then they'll shift it somehow.
Mhm.
Or that's how I kind of took this section, just like the continuity of a machine learning system.
Yeah. Shadowing is much like with continuous integration into a web service. Shadowing is a general idea that is good for stability of really large and complex software systems, which is like no matter how many tests you write and no matter how confident you are that you've improved the system, if you're working at the scale and complexity of something like Google Docs, I don't know, you don't really want to just like push to prod and suddenly change the software for all users at once without checking the behavior in production. So yeah, that kind of shadowing is one way kind of do testing, but put yourself much closer to actual production. You can both literally shadow, as Tesla does, and push inputs to a model that isn't actually making decisions or isn't actually having its perceptions being used, collect up those perceptions and do comparisons, find the places where it's most different from your previous model and confirm that they're improvements, spot check the places where they're saying the same thing, make sure that you think that they're doing well. And then also in some sense, this continual learning example where the model is continually learning, the neural network is continually learning while the collaborative filtering is actually delivering predictions. That is kind of like a really extreme form of shadowing because you're kind of like using the shadow environment to actually develop this model. Any of these other 6 tips for model selection, number 3 will blow your mind. Any other comments on these?
Yeah, number three, where it's avoid human biases in selecting models.
Mhm.
Yeah, this is definitely correct. This is the
Mhm.
one where you could have a person training two models, and because say model A and model B, and then the person's more excited about model B, and then hyper or tunes model B quite a bit more than model A, and then model B performs better. And then they say it's better than A, even though if they had done maybe equal or extensive tuning on both A and B, model A turns out better.
Mhm.
I think about this every time I read a CNU paper. There's just like tons of papers every day or every week, and then people are trying to publish or graduate or whatever, and they compare it to baselines. And I'm starting to have to figure out how they did their comparison. Is the comparison done to a baseline 5 years ago, or is it done to a comparison what you would do now? For example, like if you're training your ResNet now, there's new techniques to train it. and it's gotten better over the years. And if like I'm at the point where I look at the authors now, if it's not from a reputable author, then I probably won't really read a paper because there's just that work you gotta additional work you have to do to dig into the details. And then did this author really do this research extensively enough for me to draw a conclusion or not?
I've learned also to mistrust sometimes also the reputable people, maybe even more so than the
I do
non.
that too. But I mean, it's at least we have the more reputable people. You have like more reputable people looking over that paper, and then maybe you can
Yeah.
see someone's like other opinion on it.
Yeah, definitely. I find it really helpful to follow communities like the MLC Discord or r/ml on Reddit, or thoughtful people on Twitter who give good critiques and have strong opinions about how to appropriately baseline, say, a computer vision model. Oh, it's unfair to compare to this particular type of ResNet training because this other paper shows that it's like really, really important to incorporate, I don't know, the ConvNext ideas. Yeah, so I find those really helpful for deciding whether a technique or an architecture is worth reading about. Maybe skim it so that I know the name and can pull it back up later if it seems like it's relevant, and then wait to see how people react. Also, I found that when you search topics from papers on Twitter, you can often find that people have been chatting about it.
Oh, that's interesting.
Yeah, even though, it's kinda hard. There's like a information discovery problem with Twitter, right? There's a lot of noise and the signal is often very small. This point about engineers sort of like spending way more time on, sexier, cooler models is, I think, pretty well taken. I think really this is maybe something that's solved at a cultural level in an engineering team, of sort of like being rigorous about these kinds of decisions, or documenting how much time you spend, being very clear that you ran 100 experiments on one architecture and 2 on the other one. But, it seems like it's a difficult thing to surface in comparison to top line metrics or other things that maybe are you more often top of mind. The one thing that I've seen help is in an environment with strong regulation that forces you to be very certain of any claims that you make about your system, then people are a lot more cautious. And so this kind of information is tracked, this kind of information is surfaced, and people sort of like generally move a bit more slowly and carefully. But I think other than that, it's a tough problem. Yeah, there's kind of similar vibes for some of the other tips. Don't just always go for state of the art. State of the art doesn't always, mean it's going to be the best thing for your data. This is, I think, a general problem that people have in other disciplines of software engineering. People want to use new technologies because they're excited about them. They heard a conference talk about them. They read like a little O'Reilly book, and they're like, I got to use this new database technology. I got to use this new Python framework. But just because it solves some problem really well doesn't mean it solves, your problems very well. And relatedly, starting with the simple models is definitely, in my experience, the right move to be able to have something that you understand to compare later things to. Linear regression, a Markov model, logistic regression, a zero rule, as she puts it later, version of the system that follows some like very basic heuristic, just to give yourself some grounding, and to help you like work out bugs. All right. There's a long section on ensembling, which has some interesting stuff in it. We could talk about that. I have lots of thoughts on experiment tracking and versioning, since that's where I've worked in the past.
For versioning and I guess tracking of versioning, I'm still in the boat where it's very crude how I do it. And all right, are you still on weights and biases? Or
Not anymore.
okay, so you're not biased. Is there a tool that does both eat pretty seamlessly? Like I've seen weights and biases, and people just stick a config and you just set what you're setting that are safe to run. But I wasn't sure. I haven't seen anything with data versioning with the weight. Is there a tool? Do you know like a tool that kind of does both pretty seamlessly that may last a while? It's not like someone's GitHub that's going only
Yeah.
maintained for like a year or something.
Yeah, you definitely, with the incorporating experiment tracking and versioning, like it ends up kind of touching a lot of your code and ends up being kind of like central in your pipeline. So you definitely don't want to end up using some kind of like, yeah, vaporware from some OSS repository that some grad student is going to abandon. Obviously I've never done that. There's a nice little paragraph here that mentions this issue that Dan is bringing up, that you kind of want to do this experiment tracking thing, which is, what happened to the loss over time, what happened to the values of the gradients, the parameters, what were the outputs on a particular like slice of the validation set, all kinds of metrics and details about the optimization process and the like, hyperparameters you were trying. You want to know all that information, and you usually want it to go along with this other aspect of versioning, which is keeping track of the relevant artifacts for that experiment, where artifacts mean files that are hard to version with something like Git. So things like model files or splits of your data set. So you want to keep track of both of those things. And I think a lot of people want to keep track of them together so that you have both the information you need to, say, like recreate an experiment and also use its results. So the inputs and the outputs of that experiment. And then also the context of what happened during that experiment, so that you know when rerunning it or using its outputs is a good idea and a bad idea. So, as Chip points out, many tools that originally set out to be experiment tracking tools, like MLflow and Weights and Biases, where I previously worked, have added versioning for data sets and models to their toolkit. And then DVC, data version control, started off as a versioning tool, but now also does experiment tracking. So you can basically version the results of your experiments. The only one of these tools that I've used a ton is, unsurprisingly, Weights and Biases, since I was doing documentation development and education for them. So I can say that there's like a working pipeline for doing versioning of your data, exploratory data analysis, experiment tracking, and then model versioning. And then also like pulling those models down and using them in a deployment environment. It does do that soup to nuts, cradle to grave kind of thing in Weights and Biases. I believe MLflow has like very similar offering. There are things like this built into TensorFlow Extended as well, which is a little bit more framework specific, and also built into SageMaker. SageMaker, I think, has a separate tool for this stuff that you at least have the choice of using. But I would say that there hasn't been a consolidation in the broad world of machine learning around a particular tool for solving both of those problems together.
Yeah, my question, I guess I'll just throw it out there if anyone has experience trying like comparing MLflow, weights and biases, or just DVC or whatever new tool out there is. So for weights and biases, what did they, or when you were there or last, how did they handle their versioning, or what path did they go down? How low and like control do you need? Because I remember in some of these chapters it said even the hardware could change it. Like if so maybe the GPU architecture changed from or
Mhm.
using a different GPU or using a different process like CPU, that might even change your randomization. So it might not be your experiments might not be reproducible exactly. So how deep did weights and biases go for versioning?
Yeah. So I think there's actually kind of two separable concerns here. There's artifact tracking and versioning, and there's like reproducibility. And reproducibility is really important for certain types of engineering teams and like tracking down certain types of bugs. And like a lot of scientists care really deeply about the reproducibility of their results. Some scientific communities care really deeply about this. And
Separate.
versioning is really important for
Okay.
doing that, but you can have versioning without perfect reproducibility, and perfect reproducibility is so hard. Like you need to Dockerize everything, and then those
Okay.
like Docker containers need to be really rigid. So that's not a goal that there are people who are out there like replicate.ai, like kind of has that as one of their goals. And like Floyd Hub, I'm not sure how robust and active their development is now, but they were really pursuing that for reproducible science a couple of years ago. There definitely are specific tools for getting that level of reproducibility, but I think it's maybe a little bit separate from these versioning tools, which are really just making sure that all the models that I've trained on this data set can be like looked at once, in the same way that I can look at the history of diffs on a particular code file as a feature has developed, which is like a little bit separate from reproducible execution of a model or its experiment.
I see. So what are so for versioning? I guess were there some like fundamental questions you gotta like answer when you're trying to figure out how you want to do your versioning? Like I think I saw some of the paragraphs where you can literally check the checksum of data sets to see like there's. I guess that's a check between them, but do you know like any key ideas that weights and biases or anybody have to go through to figure out their versioning plan?
Yeah, DVC is very much so Git inspired. And oh, and by the way, the other tool for this that people sometimes use is just plain Git LFS. So you can store really large files on Git with Git large file storage, sort of like a feature you can opt into on GitHub. And the idea is that, oh, we for data, maybe when you're doing model development, the data changes very slowly. And so it's easy to just be like, check in the data and this is and add it to Git LFS. I think it gets a little bit expensive, and the ergonomics for development are not great if you're like regularly changing a really large file in Git LFS. It can slow down development or make it a little bit more difficult. DVC is very Git inspired, like it feels like using Git. You're sort of like committing and branching and things like that. Weights and biases still has the same idea of like diffing and only storing changes and using checksums to like confirm whether something has changed or not. But it doesn't feel as much like you're using Git. There's less of this like pull, push, commit, branch feel to it. They're like slightly different strategies. I don't know if I think people are still deciding which one they like best. Git LFS is really, really simple and low effort to integrate. If you already have weights and biases in your experiments, then maybe adding the artifact tracking, at least on a trial basis, is really easy and straightforward. And then DDC, I think, has something a reputation for being best in class for this specific problem, but I don't have a strong opinion on that.
Okay.
Hopefully that was helpful for your question. Daniel, as opposed to Dan, also had some questions here. Clear on what the difficulties of doing data versioning are, but I'm not sure what the standard should be. Okay, yeah, so it's actually like quite similar to Dan's question. Is that still a very open problem depending on your resources? I would definitely say that different solutions will work for different scales, and maybe even different types of problems. Like, for example, Hugging Face does offer tracking of models and data sets. Like, you can upload models or upload data to Hugging Face and then version them. Maybe, yeah, I don't know what that looks like inside of an engineering team. Like, the public stuff looks a lot more like a release. It looks a lot more like papers with code. So it's not really about this like versioning and checking while you're working and developing a model like we're talking about in this chapter. But I think you can use their tools for that. Just to give another example, and it's like really tightly optimized for these natural language processing tasks and models and data sets that Hugging Face has really specialized in. So I really do think that there is not a standard. It's maybe, I mean, DVC's been around for a while. Weights and Biases Artifacts is a couple years old. Floyd Hub is even older. Git LFS is also older. So I think it may just be that there's not one answer, just like there's not one answer for lots of other difficult cloud storage problems. I think it's not like Git for versioning code where like pretty much everybody agrees that Git is the right solution to source code version control, which is a bit of a bummer, I guess. But data is always harder, I think, than code.
Yeah, some company will come along and solve that issue. That's what's gonna happen.
Yeah, yeah, hopefully. It is just really hard to think about what it means to version a data set because just to give another example, EU citizens have the right to be forgotten by data systems. So they have a legally enshrined right to have their data removed from your server. If you're like pulling in EU citizen data, you have to be capable of doing that. And so if you're operating at a certain scale or operating, with a certain level of, actual concern for regulations, not every team does this, unfortunately, then you literally cannot do the kind of versioning that people will do for code. Like, you legally have to be able to change history. And that's something that doesn't come up as much with Git because people don't Git check in personal information directly into their Git repositories. But it is something that comes up with data. And that's just one indication of a lot of the like gnarliness of the data versioning problem.
But I mean, you could delete the history too, though, right? I mean, what? And even with Git, sometimes, I mean, I've done it, like checked in a file with the password, and then you have to delete the file from like all from the complete Git history. So, I mean, it is something that can happen, and then you can delete the history if you want.
Yeah. Well, so what the thing is though, with GitHub, you can never really guarantee. I mean, if somebody has like downloaded it to to their local Git, then it's leaked, right? So there's only so much you can do with deleting history on publicly available repositories. Yeah,
Right.
I
But at
agree.
that point, you've already made public the data, which you probably should not.
Yeah. Yeah, that's true. Like within a team, if you delete it from you can maybe put processes in place to delete it off of anybody who's pulled down a copy of the repository or a copy of the data. I would also say that it's the example that you gave is also like, oh, I accidentally checked in my password with data. If the goal of data versioning is to be able to do reproducibility for a model or to be able to back out and find maybe which data point caused a model to learn the wrong thing that it did in production. If data points can be deleted, then you no longer have that. You no longer have full reproducibility and you no longer have full lineage of the model because a model trained on deleted data may be outrunning in production. And so the reproducibility really goes out the window.
Got it.
I guess maybe we're asking for too much out of data versioning and model versioning. Maybe it's too much to ask that a training process can be recreated at a later point in time. But for other regulations, it's maybe important that certain aspects that were not tracked during the initial training can be tracked in a later reproduction of it. Hard to say.
So I had a question about, I mean, I'm kind of jumping here,
Hmm.
but you'd mentioned transformers having these rough edges, which make it due to which they struggle with, overfitting on a batch somewhere. Right.
Oh, yeah.
Yeah. I mean, I'd love to, I don't know if there is some study around it or if it's a known phenomenon.
Yeah. So just for context, this is in where are we at? The model debugging sidebar, sort of talking about the like basic forms of debugging that you do before you do full on model evaluation. So this comes from Andre Karpathy's recipe for training neural networks post, which is really rather nice. One thing that Karpathy recommends and that lots of people have also picked up and also recommend is this overfit a single batch idea, which is that, if you're trying to make sure that you didn't write the wrong thing in your model. Like you transpose some matrix and now you're not actually doing, attention appropriately. You're no longer attending over the sequence. You're doing something that makes no sense. Overfitting a single batch, the principle is that if you've implemented your model correctly, it should be possible for it to memorize one batch's worth of data. Otherwise, you might have a bug in your model, in your optimizer, in your data, etc. And I definitely think this is a way to discover bugs in your pipeline. But what I have found is that this recipe for training neural networks post is kind of old, and there are a lot of things have been added to neural networks in the intervening time. More kinds of normalization and like more aggressive use of normalization. And I think that can make it harder to run this like overfit a single batch. And my experience so far with trying it with transformers recently, just over the past month or so, is that transformers that train very, very well on the full data set just don't work well trying to overfit a single batch. And I don't have like a complete and full understanding here, but my current guess is that there are issues around normalization, initialization, parameterization, sort of like your garden variety optimization issues that hobble your attempt to do overfitting a single batch. So with certain kinds of initializations, you'll end up with a network that predicts the same thing on every input, or where the gradients are all really, really small, like close to zero. And these kinds of things really hurt your optimization. With stochastic gradient descent, where you have lots and lots of batches and the gradients are more variable, that can actually kind of paper over some of these optimization issues. And so then you end up with something that works when you have lots of batches, but doesn't work to overfit a single batch. So you might say that this means that there's like kind of like basically a bug in the transformer architecture in the same way that like early convnets also struggle to overfit single batches and MLPs without skip connections can struggle to overfit single batches. and maybe the default initializations in PyTorch have some issues. Greg Yang's tensor programs series has really kind of is the best work on that. Maybe it's that this is too strong, almost in some ways like too strong of a requirement, in that you will have models that can't overfit a single batch, but will work well in training. And given that there are maybe like lots of models that are very popular, deployed in production, used and fine-tuned that don't fit this, it's maybe unclear that it's worth the engineering time to pursue such a good implementation of the model and such a well-designed architecture that it can, in fact, both overfit a single batch and train on all of the data.
And I mean, when you said you can't fit I'm not that familiar with the NLP world, but when you said you can't fit a transformer on a small data set, like a small batch, I mean, immediately I thought, okay, there must be something that needs to be added to the transformer because I mean, it doesn't make sense. I mean, maybe it does make sense, but I don't understand that where it can only work on a really large data set. And I'm talking about training laws. Like it can only do well on a large data set, but it can't overfit on a small training set. It's a neural network. Something doesn't sound right. I mean, it's definitely missing something. So that, like you said, the MLP with the skip connections, but something's missing in the architecture. So, I mean, that's where you get this overfit a small batch, or it's just try on a small data set so you can iterate faster and figure out what's wrong. But
Yeah,
transformer, I guess you just need, someone needs to add some more stuff until it can actually overfit on a small data set, which it should. It should always be able to overfit on a small data set. If not, then something's wrong.
yeah, I guess it's important to remember that there's a distinction between there existing a setting of the weights that solves the problem and that setting of the weights being discoverable by the optimization process that you use. I don't disagree with you that there are issues with the like baseline transformer architecture, which to be clear, I'm just using the like PyTorch transformer encoder decoder in the experiments that I'm talking about here. I do think that the optimization problem is so different for a single batch where really what you are doing is you're basically doing full batch, full gradient descent, right? As though you were loading the entire data set into memory and then taking a single gradient step. That's what basically switching from stochastic gradient descent to deterministic gradient descent. And those algorithms behave very differently. So it's like not so sensible to demand that your architecture work for both stochastic and deterministic gradient descent.
Yeah, I guess when I see the overfit a single batch, what I'm thinking is try your architecture on a smaller data set. In parallel, I think that to me that always means you got to change your batch size and your learning rate as well. I mean, those come. I mean, to me, these three come hand in hand. But yeah, if you're gonna go with a smaller data set with the same batch size, I don't know if that's gonna work well. Yeah, I agree with that point.
The version of this that's like implemented in, say, PyTorch Lightning is literally you give a batch size, a learning rate, et cetera, and then you just say dash dash overfit single batch. And then it just sets the data loader so that you only draw one batch each epoch. You do want to do a little bit of hyperparameter tuning, but I think the issues here are things like normalization layers behaving weirdly if there's no variability, or like transformers have this like warm up and decay learning rate procedure, and it's unclear whether that's needed or whether that needs to be changed when you switch to overfitting a single batch. And given that you're going to make all of these kind of changes at a hyperparameter level and maybe even an architectural level, then it becomes unclear what you're really gaining by doing the overfit a single batch thing, as opposed to actually what you said, which is like train on a smaller data set. Have a data set that's maybe 10% the size of your full data set or 5% the size of your full data set. That's a very, very different thing from a single batch because single batches are usually much smaller fractions of the data set.
Yeah, so I mean, I thought that's what Andre meant. I mean, I know the wording here says overfit a single batch, but I thought it's not literally that. It's you use smaller data. I thought it's just you use smaller data and then you try to make sure your algorithm works on a smaller data set. I mean, that's the real idea. It's not literally overfit a bat. Is it?
That's at least one of the recommendations here is literally overfit a single batch, which is to say only care about the training loss on a
But
single batch.
but it's like your data set is a batch of data, but I always understood this as you're not your batch size isn't the batch. It's just that your data set is a batch size. but what your data loader batches are changing. That's how I understood like the spirit of this
Hmm.
idea.
Interesting. Yeah.
Yeah, because
I'll
I
check
know
that.
Andrew Ng says that, or if it is deep learning stuff, it's like just try it on a small data set and then make sure your
Yeah.
algorithm works. But
Yeah.
yeah, this overfit a single batch, if you are literally thinking a little batch, that's gonna cause issues. I agree.
I view it as just like a really, really high standard that's maybe unrealistically high to have an architecture and a setup that can both overfit a single batch and fit your full data. But also, you mentioned Andrew Ng. I think, yeah, the idea that you want to iterate on a small data set, I don't think there's anything objectionable about that. And I think the strongest version of that is probably like neural scaling laws, right? Like use smaller data sets and smaller models to figure out precise details of this learning problem so that you don't have to run 10 experiments at scale. You only have to run one.
think that section tells a little misleading. I mean, like one example is maybe you have to find the batch size that works for your model. So you use a smaller data set and then you're going to sweep across batch sizes. And then you figure out, okay, I need a certain percentage batch size for my model to work.
Hmm. Also, there were some questions about like references or additional detail on these like rough edges with transformers. And I think basically the place where I have found this stuff written about the most is where people propose changes to the transformer architecture. So I can actually link Boris Dama is a Hugging Face scientist who's done some experiments on different architectures and comparing them. So you can look through the architectures that he has there, see which ones are working well on his particular problem and check out those papers. I think the answer to the cause of these rough edges, I think, is like architectural issues and like optimization issues that haven't been worked out for transformers. Okay, looking at my clock, it's 10 o'clock here in California. So that's all the time that we have. Yeah, there is a nice section on offline evaluation, which is other ways of thinking about your model besides just loss. But hopefully cover some of these ideas when we talk about model monitoring as well and continual learning in the next two chapters. I got the next chapter from Chip, so I'll share that soon. And I will see you all hopefully in a week to talk about the next chapter.